The authors of this presentation are Melanie Baker, Derek Megersa, and Alfonso Panlilio, and is titled Runway Operational Quality Assurance. Our sponsors are Dr. George Donahue, Mr. Yimin Zhang, and the George Mason Catcher Lab. Looking at the top 35 airports in the country, 27 out of those 35 are at or nearing their limit on capacity. By the year 2033, they will experience a 20% or greater increase in demand, which will lead to an increase in congestion and delays on runways. The most direct way to increase capacity is to build new runways, but this is not a feasible solution at airports such as LaGuardia and San Francisco. The next best option is to increase the capacity by using existing runways more efficiently by changing the separation between aircrafts as they approach and land. This involves changes to two distributions, the runway occupancy time distribution and in-arrival time distribution, which I will explain on the next slide. The approach and landing process is where bottlenecks occur with the expected increase in capacity. Therefore, this is the scope and focus of our project. As you can see, on the left is the runway occupancy time distribution, and on the right is the in-arrival time distribution. The ROT distribution represents the amount of time aircraft spend on the runway, and the INT distribution represents the time between aircraft as they enter the final approach fix. The final approach fix is labeled FAF on the diagram and can be 3 to 8 nautical miles from the runway threshold. So far we've proposed the idea of reducing separation distances between aircraft in order to increase capacity, but with this comes a related safety risk. As aircraft approach and land, two safety violations could occur, a simultaneous runway occupancy violation or a wave vortex encounter. An SRO violation occurs when two planes are on the runway at the same time, and a wave vortex violation occurs when two planes are separated by less distance than the FAA requires. Based on ICAO standards, collisions should be on the order of 10 to the 7th to 10 to the 9th, but since the two violations are not exactly collisions, but rather just precursors to accidents, the acceptable rate of these violations should be a couple magnitudes below the collision rate at 10 to the 4th or 10 to the 5th. This graph shows the union set between the IAT and ROT distributions. This area highlighted in red represents the probability of an SRO occurring. According to the FAA, no SRO is allowed. However, studies have shown there is always a probability of SRO happening due to the stochastic nature of the arrival process. So clearly there's a trade-off between throughput and safety that we want you to take away from this graph. On the y-axis we have safety defined as 1 minus the probability of an SRO, and along the x-axis is arrivals per quarter hour. Basically, safety and throughput have an inverse relationship, and as throughput increases, safety decreases. The FAA has proposed to implement a satellite-based system to improve the air traffic control system in an effort to increase capacity. This new system is called Next Generation Air Transportation System, otherwise known as NextGen. The new ADS-B surveillance technology part of NextGen allows the precise position of aircraft to be monitored using GPS, which would allow aircraft to be sequenced precisely, reducing the variability of separation between aircraft. Visually, you can see this resulting in a narrower IAT distribution with less overlap between the ROT and IAT distributions. This means spacing could be reduced to improve throughput while still maintaining an acceptable probability of SRO. So just to give you an idea of all the people who care about this system, I'll quickly present our stakeholders. First, we have the FAA, who provide rules and regulations as their priority is to maintain safety. Next, we have the pilots, who control aircrafts, and their main responsibility is the safety of their aircraft. ATC are also responsible for monitoring safety of aircraft as planes approach and land. Then we have the airports and airlines, who own the runways and want to see an increase in capacity in order to maximize their profits. As you can see, there is a safety versus capacity tension between our stakeholders, which leads to our problem statement. Our problem statement reads that the future utilization of runways to meet the growing demand for air transportation has a risk, which is a probability of a loss of safety. Therefore, a tool such as ROQA is needed to monitor the stochasticity of the arrival process and show how changing parameters of the IAT and ROT distributions affect safety and throughput. We have 4 design alternatives, the first being to change the runway occupancy time distribution standard deviation. The second is to change the in-arrival time distribution standard deviation, which will be done by changing the ATC buffer standard deviation. The third is to change the in-arrival time distribution mean, which will again be done by changing the ATC buffer mean. And the fourth is a combination of alternatives 2 and 3, changing the in-arrival time distribution mean and standard deviation. This is a black box diagram of ROQA in order to show the inputs and outputs of the system. Our inputs are FAA standards, which include regulations on ATC buffer and SRO. And we also have surveillance data, which includes speed, runway occupancy time, and in-arrival time, aircraft info, and fleet mix of aircraft. Our outputs will be the percentage of SRO violations and separation violations and runway throughput. displayed as a monitoring report. Inside of that black box, the inputs are read into the system, stochastic data analysis is done, distributions are idealized, and the results are computed. These results will be displayed to different stakeholders in different ways based on their objectives. Because the FAA's priority is safety, they will be given a report with the idealized ROT and IET distributions, as well as violation information. Airport managers will be given the idealized distributions and safety information, as well as throughput data to ensure the safe and efficient operation of the runway. ATC supervisors will be given a colored display showing the current level of safety the airport is operating at. Lastly, airline operation managers will be given the idealized distribution, safety information, and throughput information. So now I will explain our ROQA prototype, which is a Monte Carlo simulation created using Java. The purpose of the simulation is to model the approach and landing process and show how the runway occupancy time and ATC buffer parameters affect the safety level of the runway. The scope of the system is the final approach fix, which is 6 nautical miles in our simulation, to model the Detroit airport. And our assumptions are that this is for a single runway. We're only modeling the arrival process, and the ATC buffer, airplane speed, and runway occupancy time are all drawn from normal distributions. The first step in the simulation is to generate a random string of non-homogeneous arrival flights, which means there's a mix of heavy, large, medium, and small planes. Next, each plane is assigned an approach speed and runway occupancy time. Again, these are drawn from normal distributions, with mean based on the type of aircraft and standard deviation of 5. The third step is to assign a separation distance between the lead and follow pair of flights based on the wake vortex separation distance table, and here is also where the ATC buffer is included and where compression and expansion cases are accounted for. The next step is to fly the planes in which a trajectory is generated for each plane, and we compare the lead-follow pair trajectories to decide if a separation violation or SRO violation occurred. The last step is to calculate the runway throughput. These are our results for changing ATC buffer standard deviation and ROT standard deviation. Looking at the percentage of SRO and wake vortex encounters column, you can see that the safety level decreases as the standard deviation increases in both the ATC buffer and ROT experiments. However, the interesting thing to point out here is that the throughput remains constant at roughly 35 planes. Looking at the graph where we've plotted these results, we can see that when the standard deviation of the ATC buffer increases to 7.5, this would lead to a violation of safety, as this point falls below the red line plotted to represent the accepted safety level. We can also see that changing the ATC buffer standard deviation has a larger effect on safety level than ROT standard deviation. Here are the results after changing the ATC buffer mean, holding the standard deviation constant. As the mean increases, safety level increases, however throughput changes inversely to safety. When the ATC buffer was lowest, at 2.5 seconds, the throughput was at its maximum point of 39 planes. Throughput was lowest at 33 planes when the ATC buffer was increased to 12.5 seconds. So although increasing the ATC buffer mean allowed capacity to increase, safety was sacrificed. Decreasing the mean to 2.5 caused the safety level to drop below the accepted rate of 10 to the 4th. In order to verify our simulation results are correct, we did a comparison of data between that of our ROQA prototype and a study done by Katzer. As you can see, both show a similar downward curve, which says there's an inverse relationship between safety and throughput. Differences occur as the results differ in the way they are obtained, ours by simulation and the other done analytically. Also, the graph on the right is for SRO only. Our last results where we changed the standard deviation of the ATC buffer to 2.5 down from 5 and varied the mean showed similar results to the previous experiment. However, looking at the graph, you can see that by reducing the ATC buffer standard deviation, the safety level drops slower than when it was originally 5. In conclusion, ATC buffer mean affects throughput as well as the percentage of SRO violations and separation violations. Throughput is not affected by the standard deviation of ATC buffer or ROT within the range we examined. And also, the IET distribution dominates capacity. Basically, in order to increase capacity, first we must reduce the ATC buffer and ROT variance by implementing NextGen's ADS-B. Then we must reduce the ATC buffer mean, which can be done with a change in FAA procedures. Thank you for watching this presentation on ROQA.